We can think of x bar as a random variable because it takes numerical values that describe the outcome of the random sampling process. X bar is a random variable because the value of x bar varies as per the units in the sample. We are taking a sample of 50. That 50 units will be different in different samples. Then what about x bar? There will be a value for x bar for the first possible sample, x bar for the second possible sample, etc. The value of x bar or x bar is itself is a random variable. As a result, we can examine its probability distribution. X bar is a random variable. A random variable will have a probability distribution. We can examine its probability distribution using that we learned in chapter 6. The following activity will help you get a feel for the distribution of two very common statistics, that is sample mean x bar and sample proportion p hat. A statistic means you know what is meant by statistics. That is not the subject
Yeah, so like
statistics,
the whole population.
but
Yeah, just like a value for the entire population.
that is the characteristics of the sample, right? Statistic, that is singular. Statistic. What is statistic? That is defined to be the characteristic of the sample. This one, okay?
Oh,
Statistic.
oh, I thought it's for the population.
No, the characteristic of population is parameter.
Oh, okay. Yeah,
Characteristic of the sample is statistic.
yeah.
This sample mean x bar is a statistic, while population mean mu is a parameter. Okay.
Yeah.
In this activity, your class will investigate how the mean year x bar and the proportion of the pennies from the 2000s p hat vary from sample to sample using a large population of pennies of various ages. Each member of the class should randomly select one penny from the population and record the year of the penny with an X on the dot plot provided by the teacher. Return the penny to the population. Repeat this process until at least repeat this process until at least 100 pennies have been selected and recorded. This graph gives you an idea of what the population distribution of penny years looks like. Each member of the class should then select a simple random sample of 5 pennies from the population and note the year of each penny. Record the average year of these 5 pennies rounded to the nearest year with an X bar on a new class dot plot. Make sure this dot plot is on the same scale as the dot plot on the step 1. Record the proportion of pennies from the 2000s with a p hat on a different dot plot provided by your teacher. Return the pennies to the population. Repeat this process until there are at least 100 X bars and 100 P hats. Repeat step 2 with simple random sample of size n is equal to 20. Make sure these dot plots are on the same scale as the corresponding dot plots from step 2. Compare the distributions of x, that is year of penny, the new distribution of x bar, that is mean year. How are the distributions similar? How they are different? What effect does sample size seem to have on the shape, center, and variability of the distribution of x bar? Compare the two distributions of p hats. How are the distributions similar? How are they different? What effect does sample size seem to have on the shape, center, and variability of the distribution of p hats? Now, two statistics x bar and p hat. X bar is the sample mean, p hat is the proportion. Okay, sampling distributions are the foundation of inference when data are produced by random sampling. As you know, we will be studying the population or the characteristics of the population based on a sample. Sample, what is a sample? Sample is a representative subgroup of the population, a representative subset of the population. That is sample. By studying sample, we want to make inferences about the population. Because the results of random samples include an element of chance, we can't guarantee that our inferences are correct always. We can't guarantee that. There may be variation due to the sampling. What we can guarantee is that our methods usually give correct answers. That is, the probability will be high. The reasoning of statistical inference rests on asking how often would this method give a correct answer if I used it many times. If our data come from random sampling, the laws of probability help us answer this question. These laws also allows us to determine how far our estimates typically vary from the truth and what values of the statistics should be considered unusual. Section 7.1 presents the basic ideas of of sampling distributions. The most common applications of statistical inference involve proportions and means. Section 7.2 focuses on sampling distributions of sample proportions. Section 7.3 investigates sampling distributions of sample means. What is the average income of US residents with a college degree? Each March, the government's current population survey asks detailed questions about income. The random sample of about 70,000 US college graduates conducted in March 2016 had a mean total money income of $73,750 in 2015. That is, $73,750 describes the sample, but we use it to estimate the mean income of all college graduates in the United States. As we begin to use sample data to draw conclusions about a larger population, we must be clear about whether this number describes a sample or a population. For example, of college graduates conducted by the CPS, the mean income was X bar is equal to $73,750. The number 73,750 is a statistic because it describes this one CPS sample. The population that the poll wants to draw conclusions about is the nearly 100 million US residents with a college degree. In this case, the parameter of interest is the mean income mu of all these college graduates. We don't know the value of this parameter, but we can estimate it using data from the sample. In most of the cases, the value of the parameter will be unknown. Such an entity exists. That is the population mean. Population mean will be there, but we will be uh, we won't have the exact value of that parameter. We want to estimate that parameter using a sample. A statistic is a number that describes some characteristic of a sample. Statistic is a number that is a sample characteristic. A parameter is a number that describes some characteristics of the population. For example, population mean is a parameter and its counterpart sample mean is a statistic. Okay.
Yeah.
Remember S and P. Statistics come from samples and parameters come from populations. As long as we are doing data analysis, the distinction between population and sample rarely come up. Now that we are focusing on statistical inference, however, it is essential. The notation we use should reflect this distinction. The table shows three commonly used statistics and their corresponding parameters. Statistic X bar, that is sample mean, that estimates mu, that is the population mean. P hat, the sample proportion, that estimates P, that is the population proportion. S, that is sample standard deviation, that estimates sigma, the population standard deviation. Identify the population, the parameter, sample, and the statistic in each of the following settings. The Gallup poll asked 515 randomly selected US adults if they believe in ghosts. Of the respondents, 160 said yes. What is the population here? Population is all US adults. Parameter P, the proportion of the all US adults who believe in ghosts. Sample, what is sample? The 515 people who were interviewed in this Gallup poll. Statistic, what is statistic P hat? The proportion in the sample who say they believe in ghosts. What is that proportion? 160 said yes. That is 160 divided by 550. That is 0.31. Okay.
Yeah.
Then the second one. During the winter months, the temperature outside Stannis' cabin in Colorado can stay well below freezing for weeks at a time. To prevent the pipes from freezing, Mrs. Stearns sets the thermostat at 50 degrees Fahrenheit. She wants to know how low the temperature actually gets in the cabin. A digital thermometer records the indoor temperature at 20 randomly chosen times during a given day. The minimum reading is 38 degrees Fahrenheit. What is population? All times during the day in question. That is the population. Parameter, the true minimum temperature in the cabin at all times that day. What is sample? The 20 temperature readings at randomly selected times. That is sample. Statistic means the sample minimum temperature given to be 38 degree Fahrenheit. Not all parameters and statistics have their own symbols. To distinguish parameters and statistics in these cases, use descriptors like true and sample. Many students use credit on statistics exam when defining parameters because their description refers to the sample instead of the population, or because the description is clear about which group of individuals the parameter is describing. When defining a parameter, we suggest including the word all or the word true in your description to make it clear that you are referring to a sample statistic. The idea of sampling distribution. The students in Mrs. Gallas's class did the penny for your thoughts activity at the beginning of the chapter. Figure 7.1 shows their dot plot of the sample mean. Sample mean here for 50 samples of size n is equal to 5 and n is equal to 5. 1993, 1995, 4, 2000, like that, 2005, 2010, 2015, like that. Then for 2000, I think there is only one, right?
Yeah.
Then for 1999, two are there. Okay.
Yeah.
Distribution of the sample mean year of penny for 50 samples of size n is equal to 5. That is a figure. From Mrs. Gallas. population of pennies. It shouldn't be surprising that the statistic X bar is a variable. After all, different samples of n equal to 5 pennies will produce different means. Okay, we got 50 different values. As you learned in section 4.3, this basic fact is called the sampling variability. Sampling variability refers to the fact that different random samples of the same size from the same population produce different values for a statistic. Knowing how statistics vary from sample to sample is essential when making an inference about a population. Understanding sampling variability reminds us that the value of a statistic is likely to be exactly equal to the value of the parameter it is trying to estimate. It also lets us say how much we expect an estimate to vary from its corresponding parameter. Our class took only 50 random samples of 5 pennies. However, there are many possible random samples of size 5 from the large population of that class, a large population of pennies. If the students took every one of these possible samples, calculate the value of x bar, calculate the value of x bar for each, and graphed all these x bar values, then we would have a sampling distribution. Here in this case, we have taken only 50 samples. Suppose that a large number of samples are taken and all the x bar values are plotted, then we get a sampling distribution. Sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. Probability distribution of the statistic. Remember that a distribution describes the possible values of a variable and how often these values occur. Thus, a sampling distribution shows the possible values of a statistic and how often these values occur. For large populations, it is too difficult to take all possible samples of size n to obtain the exact sampling distribution of a statistic. Instead, we can approximate a sampling distribution by taking many samples, calculating value of the statistic for each of these samples, and graphing the results. Because the students in Mrs. Galas's class didn't take all possible samples of 5 pennies. Their dot plot of x bar in figure 7.1 is called an approximate sampling distribution. The following example demonstrates how to construct a complete sampling distribution using a small population. John and Carol have 4 grown sons. Their heights in inches are 71, 75, 72, and 68. List all possible samples of size 2. Calculate the mean of each sample and display the sampling distribution of the sample mean using a dot plot. Calculate the range of each sample and display the sampling distribution of the sample range using a dot plot. We have 4. That is 4 sons and the heights are 71, 75, 72, 68. Possible samples are 71, 75, 70. We are taking a sample of 2, 71, 72 like that. Then calculate the sample mean. For 71 plus 75, mean is 73. 71, 72, mean is 71.5 like that. And we plot the sample mean on a dot plot. Then we can have 173 and 73.5. That comes closer. Then 71.5 is the 69.5 like that. Then sample range, difference between the values. 71, 75, that is 4. 71, 72, that is 1, like that. And we sample range of heights, that also is plotted. Being able to construct or approximate the sampling distribution of a statistic allows us to determine the values of the statistic that are likely to occur by chance alone, and the values that should be considered unusual. The following example shows how we can use a sampling distribution to evaluate a claim. Determine how much homework time students will get in a class. Mrs. Lin, as a student, as a student select as a student select an simple random sample of 20 chips from a large bag. The number of red chips in the simple random sample determines the number of minutes in class students go to work on homework. Mrs. Lin claims that there are 200 chips in the bag and that 100 of them are red. When Jenna selected a random sample of 20 chips from the bag without looking, she got 7 red chips. Does this provide convincing evidence that less than half of the chips in the bag are red? What is the evidence that less than half of the chips in the bag are red? Provide two explanations for the evidence described in part A. We use technology to simulate choosing 500 SRS of size n equal to 20 from a population of 200 chips, 100 red and 100 blue. The dot plot shows p hat, that is sample proportion of red chips for each of the 500 samples. There is one dot on the graph at 0.8. Explain what this value represents. Would it be surprising to get sample proportion p hat is equal to 7 by 20 is equal to 0.35 or smaller in an SRS of size 20 when p is equal to 0.05? P is 0.05, that is population proportion. She claims that 100 out of 200 is are red. Population proportion are 100 by 200, that is 0.5. Justify your answer. Based on your previous answers, is there convincing evidence that less than half of the chips in the large bag are red? Explain your reasoning. First question is what? What is the evidence that less than half of the chips in the bag are red?
Oh, actually, can we just take a 5 minute break real quick because I have to go to the restroom?
Yeah, yeah.
Okay, yeah.
5 minutes break.
Yeah, and I guess we can take a 10 minute break later.
Okay, and then you okay. We can have a 10 minutes break now.
Okay, yeah. Yeah, I'm back.
Okay.
Yeah.
Is what is the evidence that less than half of the chips in the bag are red? What is the answer given? Then the sample proportion was p hat is equal to 7 by 20, that is equal to 0.35, which is less than 0.5, right? Because
Yes.
the teacher claims that there are 100 red chips out of 200. That is population proportion is 100 by 200. That is 0.5. But what this Jenna got proportion sample proportion to be 0.35. Then provide two explanations for the evidence described in part A. It's possible that Mrs. Lin is telling the truth and Jenna got a p hat less than 0.5 because of sampling variability. That might be the reason. It is also possible that Mrs. Lin is lying and less than half of the chips in the bag are red. Two possibilities are there. Question number C. There is one dot on the graph 0.8. What happened? We use technology to simulate choosing 500 SRS. 500 simple random samples are chosen of size n equal to 20 from a population of 200 chips. 200 chips, 100 red and 100 blue. The dot plot shows we had the sample proportion of red chips for each of the 500 samples. We have 500 samples of the um, size 20, and there is one dot on 0.8. What does it represent? There is one dot on the graph at 0.8. Explain what this value represents. What this value represents? In one simulated simple random sample of 20 chips, there were 16 red chips. That is 16 by 20. That is 0.8. So p hat is equal to 0.8 for this sample. Right.
Yeah.
Then would it be surprising to get a sample proportion p hat is equal to 0.35 or smaller in an SRS of size 20 when p is equal to 0.5? Justify your answer. No, there were many simulated samples that have p hat values less than or equal to 0.35. Less than 0.35. We have this much, right?
Yeah.
Okay. Then, based on your previous answers, is there convincing evidence that less than half of the chips in the large bag are red? Explain your reasoning. Because it is in surprising to get a p hat less than or equal to 0.35 by chance alone when p is equal to 0.5. There is in convincing evidence that less than half of the chips are red. Okay, are you okay with this?
Yeah.
Suppose that Jenna's sample included only 3 red chips. Given p hat is equal to 3 by 20, that is equal to 0.15. Would this provide convincing evidence that less than half of the chips in the bag are red? Yes. According to a simulated sample distribution in the sample, it would be very unusual to get a p hat value this small when p is equal to 0.5. Less than 0.15. No values. Right. No
Yeah.
samples. No dots less than 0.15. Therefore, sampling variability would not be a plausible explanation for the outcome of Jenna's sample. If she were getting 3 red. That is the case. The only plausible explanation of p hat value 0.15 is that less than half of the chips in the bag are red. Figure 7.2 illustrates the process of choosing many random samples of 20 chips from a population of 100 red chips and 100 blue chips, and finding the sample proportion of red chips for each sample. Follow the flow of the figure from the population distribution on the left to choosing a simple random sample, graphing the distribution of the sample data, and finding the p hat for the particular sample, to collecting together the p hats from many samples. The first sample has p hat is equal to 0.4. This one. Why? The second sample is different. Is a different group of chips with p hat is equal to 0.55. Here, p hat is equal to 8 by 20. That is equal to 0.4. That is, there were 8 red chips in the sample. Here there were 11 red chips, and so on. And in the population, we have 100 and 100. Then we draw a sample of 20. Then draw another sample of 20. We get this and plot on the graph. Okay.
Yeah.
The idea of a sampling distribution is to take many samples from the same population, collect the value of the statistic from all the samples, and display the distribution of the statistic. The dot plot shows the approximate sampling distribution of p hat. P hat is equal to sample proportion of red chips. The dot plot at the right of the figure shows the distribution of the values of p hat from 500 separate simple random samples of size 20. This is the approximate sample distribution of the statistic p hat. This one. This figure. This is the approximate sample distribution. Right.
Yeah.
This graph. Terminology matters. Never just say the distribution. Always the distribution of something. Being careful to distinguish the distribution of population, the distribution of sample data, and the sampling distribution of a statistic. Right. Likewise, don't use ambiguous terms like sample distribution. We should write sampling distribution. Right. Which could refer to the distribution of sample data or to the sample distribution of the statistic. Right. The terminology should be uh, clear. You will lose credit on free response questions for misusing statistical terms. As figure 7.2 shows, there are three distinct distributions involved when the sample repeatedly when we sample repeatedly and calculate the value of a statistic. Figure 7.2. There are three distinct distributions involved when we sample repeatedly and calculate the value of a statistic. Distribution of the population, distribution of the sample, and the sampling distribution. Population distribution gives the values of the variable for all individuals in the population. In this case, the individuals are the 200 chips, and the variable we are recording is color. Our parameter of interest is the proportion of red chips in the population. P is equal to 0.5. That is for the population. Population proportion is 0.5. Okay.
Yeah.
The distribution of sample data shows the values of the variable for the variable for the individuals in a sample. Second one. That is for the sample. We have two such distributions, right?
Yeah.
Distribution of the sample data shows the values of the variable for the individuals in a sample. In this case, the distribution of sample data shows the values of the variable color for the 20 chips in the sample. For each sample, we record a value of the statistic we had, the sample proportion of red chips. Sampling distribution of the sample proportion displays the values of p hat from all possible samples of the same size. This is approximate sampling distribution, right? We have not taken all the possible samples, and this is the approximate sampling distribution. Okay,
Yeah.
that is for 500 simulated samples.
Yeah.
Remember that a sampling distribution describes how a statistic, here for example p hat, varies in many samples from the population. However, the population distribution and the distribution of the sample data describes how individuals vary. That is, for example, that is the Mars Incorporated says that the mix of colors in its M&M milk chocolates candies from its uh, Hackettstown factory is 25% blue, 25% orange, 12.5 green, 12.5% yellow, 12.5% red, and 12.5 brown. Assume that the company's claim is true and that you will randomly select 50 candies. We estimate the proportion that are orange. Identify the population, the parameter, the sample, and the statistic in this setting. Can you say what is the population?
The population would be all of the colors or all of the M&Ms in the factory. And
Yes. Okay.
and then the uh
That is the
parameter,
total production of that particular factory.
yeah, and then the parameter is the colors of the colors, all the colors in the factory,
What is the parameter?
just all of the colors that the factory makes.
No, no. The parameter is the sample proportion of orange candies. Sorry, the population proportion of orange candies. That is parameter,
Oh, so it's like 50, or no, it's like
right?
just a sample.
Population proportion. Parameter is what? Population proportion of orange candies.
So I guess then it's 25%.
No, no. Population proportion. Yeah, yeah. That is 0.25, right?
Yeah,
For what is for orange? What is that?
yeah, it's just
Uh,
0.25. It's 25% orange.
yeah, yeah. 25%. Okay, 0.25. Right, correct. Then what is the sample?
Yeah, sample would be the 50 candies that we will be randomly selecting.
Right. Then what is the statistic?
Uh, I guess just the percent of those 50 candies that are orange.
Yeah, the proportion of orange candies out of these 50.
Yeah,
Then graph the population distribution that is given. Right. Population distribution graph is given. Right.
yeah,
That is blue. How much blue?
uh,
25.
yeah,
Then 25 orange. But that is not the population. For that is not for population because for orange that is not up to that blue. This is for sample, I think. Right.
yeah.
No. For sample also that won't work. How many samples are there? 50, right?
Yeah.
Then how many units here for this frequency table? 18 plus almost 8, 26 plus 14, around 40, right?
Yeah.
That is what does this represent? This bar chart?
It's just I guess the or the in the sample of 50 candies, the number of each color that were selected.
No, then we should have 50 in total. Adding
Yes.
this we should get 50, but we won't get 50. More than 50 is here.
Oh, really? Well, if it's more than 50, then I guess it's
Yeah, it is more than 50. And also the blue and green, sorry, blue and orange. Sorry, that is for okay. For population, it may vary, no problem. Sorry, for the sample. For the sample, it may vary.
yeah.
Then I can't say what is this bar chart. Okay, we can see. Right, wait. Okay. You graph the population proportion. That is not difficult, right?
Yeah.
Like this, blue and orange will be having 25, sorry, 0.25 or 25 percentage, like that. No problem. Okay. Imagine taking a random sample of 50 milk chocolate candies. Make a graph showing a possible distribution of the sample data. Give the value of the statistic for this sample. Imagine taking a sample of 50 chocolate candies. Make a graph showing a possible distribution of the sample data. Give the value of the statistic for this sample.
Well, I guess I could just do. I don't think it matters uh what the percent of each one is, because it's just a sample. It could be anything.
Yeah. Which of these three graphs could be approximate sampling distribution of the statistic? Explain your choice. Yeah, yeah. This is the sampling distribution. That is all the three. Which of these graphs could be the approximate sampling distribution of the statistic? Sample proportion of orange. That should be in the population 25 percentage are orange, right?
Yeah.
And what could be the sample proportion of the orange
Which would
sampling
be
distribution?
25% of 50, so I guess around 12. Uh,
Right.
wait. So
The third one can be right.
wait. No, wouldn't it be the second one? Because it's close to 20, or it's close to 0.25. Or wait, how much was the orange one?
Yeah, yeah, yes, 25 percentage, right.
Yeah.
Proportion should be 0.25, around
Yeah.
0.25, right, right,
Yeah.
right,
That's down. Yeah.
right. Yes. Okay.
Yeah.
And describing sampling distribution. In fact, that the fact that statistics from random samples have definite sampling distributions allows us to answer the question: how trustworthy is a statistic as an estimate of a parameter? Here, the statistics means what? The plural of statistic. Okay, this one. Okay,
Yeah.
that means the plural of the term statistic. That is sample characteristics.
Yeah.
Okay,
Yeah.
okay. To get the complete answer, we will consider the shape, center, and variability of the sampling distribution. For reasons that will be clear later, we will save the shape of 7.2 and 7.3. 7.2 and 7.3, which is 27.2 our previous one. This is 7.2, right? And 7.3. One is 7.3. Yes, this one is figure 7.3, right?
Yeah.
Here is an activity that gets you thinking about the center and variability of sample distribution. The craft stick problem. In this activity, you will create a statistic for estimating the total number of craft sticks in a bag, that is n. The sticks are numbered. Okay, can you see?
Yeah.
In this activity, you will create a statistic for estimating the total number of craft sticks in a bag. The sticks are numbered 1, 2, 3, etc. to n. Near the end of the activity, your teacher will select a random sample of n equal to 7 sticks and read the number on each stick to the class. The team that has the best estimate for the total number of sticks will win a prize. Here the bag contains n sticks and we draw a sample of 7 and find what um, total number of sticks in the estimate for the total number of sticks. Form teams of 3 or 4 students. As a team, spend about 10 minutes transforming different ways to estimate the total number of sticks. Try to come up with at least 3 different statistics. Before your teacher provides the sample of sticks, the simulation to investigate the sample distribution of each statistic. For the simulation, assume that there are n equal to 100 sticks in the bag and that you will be selecting a sample of size n equal to 7. Using your calculator, select a simple random sample of size 7 using the command random number and verify there are no repeated numbers. If there are repeats, press enter to get a new sample. For each sample, calculate the value of each of your 3 statistics. Graph these values on a set of dot plots like those shown here. Perform as many trials of the simulation as possible. Based on the simulated uh, sample distributions, which of your statistics is best likely to produce the best estimates? Discuss as a team. Your teacher will now select a random sample of n equal to 7 sticks from the bag. On a piece of paper, write the names of your group members, your group's estimate for the number of sticks in the bag, and the statistic you use to calculate the estimate. Okay, that is the that is the activity. You got how what's to be done in this activity?
Yeah.
Okay, see, today I am stopping now because I have a meeting at 8:30, right? You
Oh,
can we can discuss tomorrow.
okay. Yeah.
You please go through the material and we can discuss tomorrow.
Yeah.
Um, Today we were having 1 hour class, right?
Well, I mean, I think we're supposed to have 3 hours, but uh,
No, no, okay, it was scheduled, but today we have taken 1 hour.
yeah.